Dear viewers, welcome back to our end-to-end demo of the autonomous driving functionality development. In this series, we are demonstrating the entire AD software development cycle, from customers' requirements to the approval for release in the target vehicle. We also describe the challenges encountered on the journey to the software-defined vehicle. The audience we are addressing are predominantly technical people, but also managers working in the area of autonomous driving. Most topics covered in this series are also applicable to other vehicle domains. In this session, I will present the current trends and challenges in software development for software-defined vehicles, or SDVs for short. They are the key motivating factor for the software development strategies and best practices shown in the subsequent videos of this series. So, what exactly will I show in this video? First, I'll give an overview of the most important trends in contemporary automotive software development. More precisely, I'll talk about the transition to software-defined vehicles and driving automation at the levels 3 and 4. Next, I'll explain the consequences of this transition and the challenges that accompany it. Let's first look at the publicly visible effects of the transition to software-defined and autonomous vehicles. For clarification, by software-defined vehicles, or SDVs, I mean vehicles whose features and functions are primarily managed by software. For the end users, they bring a range of benefits. I'll mention just the most important ones. The possibility for the owner to add new features to the vehicle anytime after the purchase. Frequent software updates, which quickly fix any bugs and security holes discovered. More advanced connectivity and richer infotainment options. Finally, software-defined vehicles may also offer the users a pay-per-use option, where functions and content activated on demand are paid only for the time they are actually being used. For the automotive OEMs, software-defined vehicles bring the opportunity to generate revenue from the aforementioned content and functions on demand, as well as from personalized advertising and data monetization. The other prominent change is the introduction of the autonomous driving functions on the level 3 and 4. The first automated driving functions coming to the market are the level 3 highway pilot and level 4 parking, with further functions expected to follow. Behind the scenes, these trends have profound implications on the technical and organizational level. Compared to traditional vehicles, software-defined ones are typically implemented with a smaller number, but more powerful electronic control units, or ECUs for short. Their components are highly interconnected, and these interconnections cross the boundaries of individual vehicle domains, and therefore the ECUs that host them. The implemented functions need to be enabled and disabled dynamically, and that may also include safety-relevant functions, like those related to the driving assistance or automated driving. New functions, as well as updates for the already installed ones, need to be delivered over the air. All of this, along with more advanced connectivity options, makes software-defined vehicles more exposed to cyber attacks, which requires the appropriate cybersecurity measures to be implemented. For automotive Tier 1 suppliers, the transition to software-defined vehicles brings the need to make their products and solutions more hardware-independent and to expand their offering towards software platforms. Highly automated driving, on the other hand, introduces a completely new class of algorithms, whose complexity exceeds everything previously seen in serially produced road vehicles. These algorithms have to operate within very narrow error margins, because neither the false positives nor the false negatives are tolerable in highly automated driving. This stands in clear contrast with the driver assistance systems, where false negatives are largely acceptable, due to the presence of a human driver responsible for correct driving and vehicle operation. This difference imposes substantially higher testing requirements for highly automated driving systems, compared to mere driver assistance systems. Let's now take a closer look at the consequences of the trends I just mentioned. As we will see, they create a cascade of issues which lead to some significant challenges for the corresponding software development. We have seen that the number and the sophistication of software functions is continuously growing. This is directly reflected in the increasing complexity of the system and software architecture of SDVs. Simultaneously, the complexity of algorithms employed in autonomous driving functions of levels 3 and above is growing at an even faster pace. As a result, it is estimated that the size of the automotive software has increased fourfold between the years 2010 and 2020, from roughly 50 to 200,000 lines of code. A similar trend is expected to continue in this decade, with Level 5 autonomous vehicles requiring up to 1 billion lines of code around the year 2030. Obviously, a larger and more complex software requires a larger team to develop it within a predefined amount of time. Developing software-defined vehicles with autonomous driving functions typically involves several thousand developers. On the other hand, it is a well-established fact that the performance of a team does not scale linearly with the team size. This forces large teams to be split up into relatively decoupled domains and small groups. In most cases, the code developed by different teams and especially different domains is integrated in the actual target hardware, which is available towards the end of the project and in limited quantities. This causes a significant amount of software integration and qualification tests to be performed late, leaving little time to fix the discovered issues. Some of these defects unconditionally have to be fixed before the release. Among such critical defects are almost all safety-related issues and deficiencies in the AD functions of Level 3 and above. The later a defect is discovered, the more time it typically requires to fix. Most of this time is spent in finding the underlying cause and ensuring that the implemented fix does not cause any regressions. Repeated often enough, this process can exhaust any available time buffers and cause product launch delays. Given that the full development team needs to be maintained until the end of the testing phase, also the development costs can easily exceed the plan. Finally, the delayed start of production may also cause a part of the expected revenue to be lost. The end result of delays in product launch, unbounded development cost, and lost revenue is clearly not acceptable from the business point of view. Yet the gap between the demand and the capabilities in automotive software development is only expected to grow in the upcoming years. It is therefore imperative to act now and start closing this gap. In this session, I have outlined the challenges related to software development for SDVs. In the next session, I will present the key strategies for overcoming these challenges. Please check the description section below for the links to other videos in this series. Don't forget to subscribe to get notified when we publish a new video. We always appreciate your feedback. If you liked this video, please press the like button. You can also leave your comment below or get in touch with us using the contact form on our homepage. Thank you for watching.